Okay. Hi, everyone. Welcome to the fourth session of the Expert Exchange series. Today we have with us Professor Hao Zhang, who is an assistant professor at UCSD. He runs the How AI Lab and also co-founded and runs the LLMs org. Today, Hao will talk about his group's recent work on LLM inference and serving called DistServe. So if you have any questions during the talk, please drop them in the comment section and we'll take them either during the talk or at the end. With that, I'm going to hand it off to Hao. Please take it away from here.
Cool. Yeah, thank you, Supriya, for the introduction, and thank you, Petros and Meta, for this great opportunity for us to share our latest work, both in my lab, also in the vLLM community. Yeah, let's get started. And the talk title is "Throughput is not all you need." I'm going to talk about how we can maximize goodput in LLM serving using prefill decode disaggregation. Okay, we all know that LLM is now the biggest thing, right? And it can enable so many new and interesting applications. And GPU is one of the most important resources today to make sure LLM runs. But we all know that GPUs are super expensive. Therefore, in the LLM inference world, all LLM service or endpoint providers, they want to minimize the cost of serving LLMs because that will translate into lower dollar per query, which will then make a high margin for profits. And this is also the key to the success of many LLM-based business. Cool. And in order to minimize the cost per query, the most popular LLM serving engines today all focus on improving the metric, which we call throughput, which basically measures how many requests or tokens you can serve per second on a given amount of GPUs. And in this talk, we ask the question, is throughput really a good enough measure considering the rich diversity of LLM applications today? And many LLM applications are offered as a service provided to users. For such services, besides the throughput, we do have some equally important metrics, which we call service level objectives, or in short, SLO. I think that's a pretty familiar word. And in LLMs, there are two most important service level objectives. I donated as a TTFT and TPOT here, and I will explain these two terms later. And let me use an example to explain, okay? In this example, a chatbot needs to have a relatively fast initial response, or TTFT, which stands for time to first token, TTFT. And in order to make, and it needs to have a relatively fast initial response in order to make the user experience better. But after it generates the initial word, the following generated text doesn't have to be faster than the average human reading speed, which means that the TPOT, which stands for time per output token, after initial token generation, doesn't have to be too fast, and you can still make a pretty good user experience. And in contrast, users who use a summarization application can tolerate a longer initial response time. But in the subsequent generations, we want it to be fast because we want to see the final summarized report as soon as possible, right? So then the question is, in the presence of meeting these two SLOs on TTFT and TPOT, is throughput a sufficiently good metric for LLM serving? It turns out that this is not always the case. And suppose we have a system that can serve 10 requests per second, okay, as I showed in this figure. But when we pose an actual constraint on TTFT and TPOT, here I use basically the dotted red line to notate the constraint I put. And we can see that only 3 requests survived under both criteria, under both SLOs. That is 3x less requests that we can serve without breaking the service level objectives. And we call the portion of throughput that is subject to the latent constraints goodput. We give it a name, goodput. And the term goodput actually can remind you of some old networking stuff, like in the old networking days, when people optimize packet delivery or video streaming quality, they have a similar metric like goodput. And LLM serving indeed share some similar idea here. So, and in this case, I want to highlight the core problem that in this talk, that is high throughput does not always translate into high goodput. And this leads us to ask an important question, like why do existing systems fail to achieve high goodput? Let's take a step back and understand how a request goes through the contemporary LLM engines. So when a request comes into an LLM inference engine like a vLLM, the system will first take the user input and generate the first token. And this process is called a prefill. And after prefill, the request starts to generate the rest of the text token by token until it finishes. And this process is called decode. And actually, I present a pretty nice visual here showing this process prefill and decode. And a request usually consists of one prefill step and multiple decoding steps until it terminates. And the popular LLM serving engines, such as vLLM, TRT LLM, they usually batch prefill and decoding requests together using a very, very famous technique called continuous batching. And if you Google continuous batching, you can find a lot of articles describing this technique. But essentially, what this continuous batching does is it allows us to batch multiple requests together for one iteration, and it allows us to mixing prefill and decode together, so it can effectively enhance the overall throughput. However, what I want to point out in this talk is the two phases, prefill and decode, they actually have very distinct characteristics in computation. So let's see what happens here. So prefill is very compute bound, meaning that a small batch of prefill or even a simple long prefill, long prompt will easily saturate the GPU computation. On the other hand, decoding actually needs a much larger batch size to hit the computation bound, because in decode, you only compute on one token at a time. And decode is also more easily subject to the memory bandwidth limit of the current generations of GPUs. So because continuous batching co-locates prefill and decode, so the two phases actually interfere with each other. Let's see a comparison here. So on the left, we batch two requests, R1 and R2, together on one GPU. And we can see that in the basically the pink window, when R2 request 2 arrives, R1's decode time, which I basically use those blue bubbles to visualize, it gets significantly prolonged. Because of R2's prefill, similarly R2's prefill, which denoted as green bubbles, also get slightly increased because of the blue bubbles, right? Because they are put together. But on the right-hand side, because we can separate the two requests, R1 and R2, onto different GPUs, we can see we can actually eliminate this interference, because the R1, which is R1's decode, which is the blue bubble, and the R2's prefill, which is the green bubble, they are now located on different GPUs and they run independently without interference. Okay, and this is a pretty nice example to illustrate this interference caused by continuous batching. And this is even worse when the system receives an incoming stream of requests. Here, if you see the red figure, we have 4 requests, R1, R2, R3, and R4. And suppose we look at the figure on the right, now the request in the decode phase gets significantly delayed every single time when a new request comes into the system, right? And as you can see, R2 actually interfere with R1, and then R3 interfere with both R1 and R2, and R4 interferes with R1, 2, 3. And I think you get an idea. Yeah. As a result of this interference, when services must satisfies both the TTFT, time to first token, and TPOT, time per output token, SLOs, system have to provision more resources to meet the latency goal, and especially when either SLO is strict. Okay, so in this example, in order to meet this SLO, we have to condense the bars, right? We need to add more compute in order to condense these bars. And in this example, we increase the number of GPUs from 1 to 4, and we managed to condense especially the green bar to a shorter one. And this lets the system barely satisfies the latency requirement at the cost of allocating more GPUs. So there's one more problem with co-location, which is a parallelism strategy. If you are familiar with language model, you probably know that there are quite a lot of different parallelisms, such as tensor, pipeline, and data parallelisms we use. And the problem here is the parallelism strategies we used are inherently coupled for the prefill and decoding computation if we co-locate them together, right? Because they locate on the same GPU. We can only apply one parallelism on one GPU. And remember that prefill and decode has distinct computational patterns. Because of this, the optimal parallelism strategy for the prefill and the decoding phase is usually different. For example, when time to first token latency is tight and the time per output token TPOT is loose, then the prefill phase probably prefers adding more tensor parallelism to meet the tight latency target, where the decoding phase prefers data or pipeline parallelism to basically boost the throughput. And if we co-locate prefill and decode, we can only apply one type of parallelism to both phases, and we don't have a choice to configure parallelism strategy for them separately, and that's a problem. So to summarize, co-location causes two major problems. The first one is the interference caused by continuous batching, right? And when you have more and more requests, the interference will get more and more pronounced. And the second problem is they have a very coupled parallelism strategy, which is not always optimal for applications with different latency criteria. Okay, therefore, I spent 10 minutes to illustrate this problem, and we start asking the question, is there a better way to achieve better goodput per GPU? And I want to present our solution, which I call disaggregated prefill and decode. And this solution is actually very, very simple. As you can see from this visual, slightly modified visual from the previous one, we simply just disaggregate prefill and decode into different GPUs. That is, we place them on different GPUs. As you can see from the animation, now the request first goes into the prefill worker to finish the prefill computation, and then the system will migrate this request from the prefill worker into the decode worker, and then the decode worker starts decoding until it finishes the generation, and then we evacuate this request because it finishes. This looks pretty simple, but let me explain the rationale behind the thing. So let's say a very, very concrete example why this simple strategy would give us improvement. And this is a real profile we did from the older version of vLLM. And to start, let me explain what this figure tries to convey. So in both these figures, the x-axis is keep increasing, and in the x-axis we are increasing the request rate gradually. That is, for example, in here you can see the request rate to a system is increasing from 2 to 3 all the way up to 10. That is 10 requests per second coming into a system. Where this y-axis is basically the P90 latency. Like in this figure is P90 TTFT, and in this figure is P90 TPOT. Okay, and we can see from the upper figure that in this real profile, this system can support roughly 3 requests per second, right? That stay within the TTFT latency constraint using one GPU. Okay, here the latency constraint is we want like 90% of the request has a TTFT that is less than 400 milliseconds. Okay, and similarly for the TPOT, based on this profile, we can see it can sustain 1.6 requests per second. That is 90% of requests has a TPOT that stay within 40 milliseconds. Okay, and therefore the overall system goodput is just the minimum of these two, right? Which is the minimum of 3 and 1.6 equals to 1.6 requests per second per GPU. Okay, that's the goodput that we can sustain by allocating this amount of like a GPU, actually a single GPU. But if we disaggregate, what happens? We can see that things actually get significantly improved. So first, because we are free from interference, we can observe that both the green curve and the blue curve somehow get a little bit flattened, right? You can see this green curve compared to this yellow curve, it get a little bit flattened. That means because we remove interference, so as a request rate increase, we can actually, for more requests, we can meet their latency. And similarly for the blue curve, it gets slightly flattened than it's like a yellow curve on the left. Okay. And now each GPU only needs to handle one type of tasks. As you can see, the prefill can achieve basically 5.6 requests per second, and the decode can basically achieve 10 requests per second. Okay, and what's more important is that now we can flexibly allocate different GPUs and parallelisms for prefill and decoding phases. Here we simply allocate 2 prefill workers, that is 2 GPUs, to pair with 1 decode worker, And we use a very simple term called 2P1D, okay? 2 prefill worker, 1 decode worker. With all 3 GPUs together, in total, we get a 10 requests per second for the whole system, okay? Right? Because here, if we allocate 2 prefill, we can sustain a maximum of RPS of like a 11.2, right? And for this one, we allocate 1, it's 10, and we still take the minimum, that is a mean of 5.6 times 2 and 10. And we take a minimum, we basically get a 10. And then we divide it by 3 GPUs, and we get a 3.3 requests per second per GPU. And this very simple strategy gives us a 2x goodput per GPU, right? Speed up. And we can actually make this way more complex and more optimized by optimizing different parallelisms against the prefill, the decoder worker, and against the different kind of latency constraints. You can arbitrarily tune this number depending on your application, right? Because different applications have different SLs. And I won't dive into that because it's a little bit more complex. But if you are curious, feel free to check our paper. Okay. We actually start implementing and rolling out this idea, and we implement this on top of vLLM, which is on top of PyTorch. And as you can see, this slide actually give you an overview of the architecture. We have a controller which will basically dispatch requests, and it will, of course, first dispatch those requests into a prefill instance. And this prefill instance basically like orchestrating quite a few GPUs with a parallel runtime built on top of PyTorch. Like in PyTorch, it's very easy to implement the different kinds of parallelism, such as tensor data and pipeline. And after the request finishes life cycle on the prefill instance, we try to migrate the request from prefill to decode. And this migration is basically done using torch distributed synonym resolve libraries and a few RPC calls. And after migration, the request will live on this decoding instance, which is another set of GPUs being orchestrated using parallel runtime that implement on top of PyTorch. Okay. And with this idea, we implement some initial prototype on top of vLLM and evaluated it against the baseline vLLM, and we tested our system on 3 different workloads and datasets. And each of them has a very distinct latency constraints. Here we have 3 different kind of chatbots, 1 code completion and 1 summarization. And our result shows that we have a pretty consistent goodput gain, ranging from 2x to 4.5x. And if you are curious, see our paper for more information. Okay. With that, I want to summarize this technical talk and start accepting questions. So to summarize, we are actively integrating this as a major feature, like that is disaggregated prefill decoding into vLLM. I think there are quite a few PRs now in vLLM that is doing this. The point I want to make in this talk is basically we should optimize goodput instead of throughput, because each application has definitely have different latency constraints. And the disaggregation is an effective technique to optimize goodput. And we build a prototype system, DistServe, that achieves 2.x to 4.48x compared to the vanilla vLLM. And we are integrating into vLLM community, and I think some other frameworks are also considering integrating this technique. And this technique, from what I learned, already adopted in many companies, including Google. And if you are interested, feel free to check out our paper and also the community updates. Cool. Yeah, that's pretty much my talk today.
Awesome. Yeah, thanks, Hao, for the presentation. I think it was very insightful. I guess we can take questions now from folks in the meeting itself.
Hi, this is Ke. Nice talk. I'm from Touch.Distributed. I don't know, if there's any comments from public viewers. I can give priority to that first. Yeah. But if no, can I ask a question?
Yeah,
I don't see any questions yet. Yeah, so go ahead.
Cool. So by instance in the figure of you have prefill instance and decode instance. By instance, do you mean a host or just a specific GPU?
It is actually a worker. I mean worker. For example, a worker can compose of multiple GPUs, and this GPU are orchestrated in a way following certain parallelism. Yeah.
I see. So how big a chance of you see of the prefill worker and the decoding worker can co-locate in the same machine such that the KV cache transfer can be fast, or would it be a case where the KV cache transfer have to go across machines?
Like if your serving workload is like medium or small scale, I think there's no problem. You just put them into the same GPU and trying to leverage decode. For example, in the recent framework SGLang, they implement this prefill decode aggregation, disaggregation, and they actually put them together on different GPUs inside of the same box. Okay, but if your workload is pretty big, for example, at Google scale, what I learned from Google is they have a lot of requests and traffic. They basically scale up by putting those on different devices across nodes. Yeah, and they have some mechanism to augment the communication. Yep. Yeah.
Sounds great. And in case it's in the same machine, is there any practice that consider just using shared memory between the instance? And like when the prefill worker is writing into the KV cache, and that's directly visible from the decoding worker, and you don't actually have to do any communication?
Yeah, in our prototype implementation, we don't do that because it's a little bit more complicated. Especially you want to share GPU memory between two processes. I think that's a little bit like a trickier. But I see no problem if you are able to implement that part. Actually, in our follow-up work called MaxServe, we did something like that. Yeah.
Cool.
Yeah.
Thanks.
Yeah. Yeah.
I had a quick question. Is your general finding that for prefill, you prefer tensor parallel, and then for decoding, you prefer pipeline parallel? Is that correct?
Yeah, that's an example. So in general, like prefill takes more time to compute, right? And decode takes like less time. And in many applications, especially in those long context applications, you observe that usually prefill latency is your bottleneck. It's very hard to meet the latency on prefill. That's why like you probably prefer to allocate more GPU for tensor parallelism to run prefill in order to meet that latency. But for decode, in general, I feel there's no compute bottleneck, and you can always meet latency pretty easily. Yeah.
Okay. Thank you.
I think we have a couple of questions from the live stream.
Okay, one question: what will be the next step for this work? Yeah, that's the next question. So we have this set as a priority in the roadmap of vLLM in this quarter. I think in Berkeley and UCSD, we allocate a few students working on adding this into vLLM. I think in SGLang, they already added some sort of implementation. Yeah, that's the plan. Yeah. So the question, for a given workload, will the disaggregation be static? Will there be a situation where we have to dynamically allocate resources, more resources to decoding? Yeah, that's a really great question. If your workload characteristics are always changing, like different applications comes at a different time, and they like have varying like prefill lenses, like decoding lenses, then yes, you should do like a reallocation of resources, and you should run algorithm to figure out what is best for the current traffic. Here in my talk, I'm making a simplified assumption that is, you know your workload, and your workload is not going to be changed, or like you allocate dedicated resources for that specific workload. Then you just need to do it once ahead of deployment. Yeah.
I guess I have one question. I'm curious if there is any requirement for like DistServe as a technique to be integrated into any serving engine that exists today.
I don't think you need any specific things. The part I felt the dirty part of DistServe is a little bit more complicated than techniques like chunk prefill, this kind of techniques. But DistServe also has its cons, that is it's very friendly to latency. And if you have latency constraints, then consider this DistServe. And also, one more thing is usually for DistServe to show its pros, you have to run serving on more than one GPU. Yeah, but I think in open source, most people probably only have access to one GPU, and they consider something that is light. But in big corporates, I believe this is much more doable. Yeah.
I have one more question. Since we have to transfer the KV cache between instances, would there be any need or advantage of like quantizing the KV cache value, or is that already been done today?
We haven't done that, at least in vLLM. It's a work in progress, but I get your point. If you are able to quantize KV cache without hurting the performance, it will also largely benefit DistServe because migrating KV cache takes some time. Yeah.
Great, thanks.
I think this is a similar question to your first one. Okay, also I'm Driss on the PyTorch team. Yeah, I was curious if it seems like the migrate step is like the increased overhead for this technique. Yeah, is it beneficial to group prefill and decoder workers on the same node as opposed to completely disentangling them, where that migrate step can increase?
Yeah, that, like I said, first it depends on how large your workload is. Like if you are able to put them inside of one NVLink, like that is you don't need more than 8 GPUs, then you are good. Yeah. But if your workload is really large, like you always want to allocate a large center party for prefill and the rest for decoding. There are two ways to think about this problem. One is how you design parallelism. You can design in a smart way, that is the center party will communicate within a node using Nico and a NVLink, but the migration between like prefill and decoder workers, they connect through network, but they are just one-time communication, so they can go through a network. Another way of thinking this problem is the migration only happens once, right? But in the life cycle of whatever request, you prefill once and you decode many times. As your decode grows longer and longer, this migration time actually overhead get amortized over your decoding steps. It becomes less obvious. Yeah, but your decode, if your decode is only like 1 token, 10 token, yes, it's a big overhead. Yeah,
that makes total sense.
Yeah. Yeah, the question, can DistServe maintain a performance improvement across different hardware configurations? How deep? That's a great question. I think after DistServe was published, there are quite a few follow-up works, and they are pursuing a more aggressive way. That is, they use different types of GPUs for prefill and decode. For example, for prefill, like I said, it's compute bound, so I want H100. But for decode, I want I want more memory. I don't care about the flops, so I use I'm not sure if you know this. In China, there's a GPU called H20 or H80. It has a lot of memory and it has less flops. And they do this kind of like a disaggregation, and they can observe even more like improvement in terms of like, for example, dollar per query. Yeah, because H80 is much cheaper than H100. Yeah. Do you say a use case for mixed workers? Splitwise is another work that you. Yeah, Splitwise is pretty similar to us. I think Splitwise is basically our concurrent work, and we also learn a lot from Splitwise. In terms of the question, mixed workers, yeah, I know there are some companies doing mixed workers. Yeah, like using slightly more heterogeneous GPUs, and one for prefill, the other for decode. Yeah.
I have a similar question because prefill and decode have two different characteristics, like you mentioned. One is compute bound, the other is memory bound. Would there be a chance to actually, how to say, overlap them in time, like running them at the same time, and they kind of like complement each other?
Yeah, I think that's essentially the idea of chunk prefill plus piggybacking. So they try to chunk a long prefill into many small chunks, and then they merge the small chunk and a few decodes together. So this mixed batch can, for example, separate the GPU or flops together with separating the memory bandwidth utilization. But the problem with chunk prefill is it will give you optimal throughput, and you can prove that. Yeah, because your GPU is always like full of utilization. The problem is it cannot meet your latency because you always put decode and prefill together, and your decode will be delayed. Yeah.
Makes sense. Totally makes sense.
Yeah.
Any other questions? We have about a minute more. Yeah, I was actually curious what other like interesting research your lab is looking into in this space, or what's coming up.
We are continue developing vLLM. We are supporting like Meta's new models, Llama 3.2, right, which is a multimodality Llama, and it causes a lot of trouble in vLLM, to be honest. We are trying to optimize the system. We are also looking into the recent like like inference time compute, like because people tend to spend more flops at the inference time and try to search different branches, right? And we believe there are some opportunities, so we are also looking into that. Yeah. Cool. I think Adam posted some new chips that probably will benefit from DistServe. Yeah. If you do heterogeneous like setup. Yeah.
Cool. Yeah. Any feedback or suggestions for the PyTorch team here, since we're all here? Anything that we could be doing better to support researchers and your lab better?
Yeah, I think PyTorch is great, and we actually did a lot of cool projects on top of PyTorch, and thanks to PyTorch for providing such a great like community and API and documentation. We are also in great touch with different PyTorch team, especially Torch Compile, trying to incorporate that into vLLM. Yeah, no complaint, I would say. Yeah.
Awesome. All right. Looks like there's a last question.
vLLM updated their performance 2.5, reducing the performance gain should in the paper will persist. I think that's orthogonal because before this like 0.6 release, vLLM has some inherent overhead on the CPU side. That is a scheduler or like some system implementation has problem, and vLLM basically fix those problems and become like a good again. And but the technical operation here is orthogonal from that. Yeah.
Okay. Awesome. Any last minute thoughts from folks here? All right.
Yeah, great talk.
Thanks.
Yeah.
Cool. Thank you.
Awesome.
Yeah.
Yeah.
Thank you guys. Yeah.
Thank you.
Thanks a lot, Hao. Yeah,
Yeah.
really appreciate you taking the time and talking to us today.
Cool. Thank you.
Bye.
Yeah.
Bye. Thanks.
Bye.